Okay, and in this slide, we will briefly discuss how we actually measure current and potential difference in circuits. Okay, so how do we measure the current? So take a look at the figure here. We have the EMF device connected to the resistors, and then there is some symbol with the letter A. This is the device to measure the current, and we call it an ammeter. Okay, so we are measuring, the ammeter is the device to measure the amperes. That is why we call it ammeter. Okay, and in fact, there are many things you have to understand. To measure the amount of current correctly, the ammeter should not affect the amount of current, right? So when you try to measure the current and then effectively change the current, that's not going to work. So the ammeter should not change the amount of current flow. So therefore, important thing is that this ammeter should be connected in series to the part where the current will be measured. Why? If you make the connection in parallel, then the current will split into different branches. So effectively the amount of current may change, right? So, and then you also want the current to flow through your ammeter so that the device can measure the current. So that is why the current has, that is why the ammeter has to be connected in series. So it's just like you cut the wire and then insert the ammeter here. So you can say that this ammeter here is measuring the current flowing from B to A. Okay, and in fact, when you do that, there's one more thing you have to be careful. Any real device will have some resistance. You cannot really make a device with perfectly zero resistance. Okay, and then you see that when you connect this ammeter in series, according to what we have learned in the previous slide, you are adding the resistance. So the total resistance may increase. If that happens, then the total amount of current may again decrease, right? You do not want that to happen. So therefore, the ideal ammeter will have zero resistance, right? And of course, in real life, there is nothing ideal. So the ammeter will have some resistance. But if you make a good ammeter, you will make its internal resistance as small as possible. Okay. And then now, how do we measure the potential difference? Oh, okay. So here, suppose now we are trying to measure the potential difference across the resistor R1. And then, how do we have to connect the device, and what kind of device would that be? We call it a voltmeter. So, which is a device measuring the voltage, okay? And then take a look at here. So this device with the letter V is the voltmeter, and then it is connected to this R1 in parallel, right? So it's connected to C and D. So it is effectively measuring the potential difference across this resistor R1, or you can also say that it's measuring the potential difference between two positions, C and D, okay? So here again, when you are trying to measure the potential difference correctly, a voltmeter should not affect the potential difference. You do not want to change the potential difference you are going to measure, right? So therefore, in this case, you have to connect the voltmeter in parallel to where the potential difference will be measured. And when you do that, we have learned that, so there is for example, there is a node. So when the current is flowing, so current flowing through R2 will be split into two currents, right? So then if that happens, then, and if there is some resistance inside this voltmeter, then what could happen? So total resistance between R1 and this voltmeter are connected, because they are connected in parallel, the total resistance may be decreased. So therefore, the amount of the current may increase. And then if the amount of current increase, then the potential may be changing. So that's what you do not want. So effectively, you have to block this current from flowing into the voltmeter. Then what do you have to do? So similarly, you can say that the ideal voltmeter will have infinite internal resistance so that no current will flow through the voltmeter. Okay, this is the case of the ideal voltmeter. But of course, again, in real life, real voltmeter will have some resistance actually smaller than being infinite. So you can say that if you make a good voltmeter, it will have a very large internal resistance. Okay. And in daily life, typically if you go to a market, you can easily buy a device looking like this, which is called a multimeter. So in this case, a multimeter is meaning that it's measuring multiple things. So it can measure ammeter and voltmeter together, but actually not at the same time. So there's a handle here, so you can actually select whether you will measure ampere or whether you will measure volt. So depending on what you want to measure, you have to understand how you would connect this device to the circuit. If you're going to use it as an ammeter, remember you are connecting it in series. If you're going to measure the voltage or potential difference, then you have to connect it in parallel. Okay. And then if you know how to measure ampere and voltmeter, then if this device knows how to measure ampere and voltage, then it can effectively measure the resistance. So therefore, it is why it is called the multimeter, measuring many things. Okay. Okay, now we will try to include a capacitor to the circuit. This is the first time we combine the resistor and a capacitor. Okay, and for that purpose, we will again use this simulated experiment provided by the PHYS152 program. So in here we have a circuit with the battery and two switches so that we can control the flow of the current. And then take a look at here. So we have a parallel plate capacitor. We have seen this parallel plate capacitor in one of the simulated experiments previously. Okay, and then where's the resistor? In fact, this light bulb will work as a resistor. It needs a resistance in order to create the light. Okay, and in fact, we have a resistor here, and then we could have used this, but in fact, this light bulb is a little bit more convenient than the resistor itself because you can see what is going on immediately in the form of light. Okay, and then two more things. This device is in fact the voltmeter. Okay, so you see that this device is connected in parallel to the capacitor. Okay, so here is connected on both sides of the capacitor. So here it will show you the potential difference across the capacitor as a function of time. Okay, so x-axis is time and y-axis is voltage. And then what is this? How about this? This is actually the current meter or ammeter. Okay, so it is connected to this part. So it has only one wire, but try to think that it is actually two wires and insert it here. So it will be measuring the current going through this position as a function of time. Okay, that's what we are going to observe. Okay, and let's move on to the real experiment. Okay, in this experiment, including a capacitor, what we want to study is the behavior of the current as a function of time. When we had only the resistor, the current didn't change with time. And of course, remember that current implies some kind of change in time because the current was the time derivative of the charge. But according to the Ohm's law, the current itself did not change with time, right? V was simply IR. But when you have a capacitor in a circuit, now the current will change as a function of time. Why? Because inside the capacitor, the charges will be accumulated. Charges will not only pass, but they will be actually accumulated, and depending on how much is accumulated, there will be a change in the Coulomb force and everything. So behavior becomes a little bit complicated, and things will change as a function of time. And that's what we are going to see here. Okay, so in the beginning, let's turn on the simulation, and then as you can see here, the here the time is flowing. Okay, you can see on this voltmeter and ammeter the times are flowing. Okay, and then right now there is no current flowing. The current is 0. Why? Because the switches are open. So for the current to flow, then well, there's no more way to go. Okay, it's stopped here. So let's close the switch, then the current will start to flow, right? How it will flow? Okay, then you see that the light is coming out from the light bulb, and then you can see the charges are being accumulated on the parallel plate capacitor, and at the same time you can see, okay, what happened to the current? Here the current suddenly changed a lot, and then it's gradually coming back to the 0, and then in the meantime you can see that now the current is almost stopped, and then there's no light coming out from the light bulb, meaning that no current is really flowing. But how about the voltage? Voltage started from 0 across the capacitor. Now voltage is almost 10 volts, or maybe 9 volts to be precise. And then the reason is because now the charges are accumulated on the parallel plate capacitor. And then how is it accumulated? You see that it's directly connected. Not directly. It is connected to this battery together with this resistor. Okay, so there is some kind of potential difference. Okay, and then let's see what will happen if I again open this circuit. If I open it carefully, nothing's happening, right? So because originally the current is already stopped, so cutting over here didn't do anything. Okay, and then how can I release these charges in the capacitor? There's another switch here. This another switch. If I close this switch, now the current will flow through this loop. Okay, so let's try that and then see what happens. Now you see that again the light is coming out, and then there's a strong surge of current, again slowly going back to original value, and then now the charges are disappearing, and then the voltage is coming back to 0 as a function of time. Okay, that is what is going on. So let's try it again. So to do that we have to be careful. We have to open this switch again, and then let's close it. Close the first switch back. Okay, now the current is flowing over here, and then take a look at the current. So current here is displayed as a negative value, and this negative value actually means that current is flowing counterclockwise, but the voltage is positive across the parallel plate capacitor. Okay, and then again I will open it, and then again close it. Okay, now it's coming back, and then try to remember the shape of this curve. The shape of the curve looks similar between the current and voltage. Not exactly the same, we will see, but they look similar. Okay, and well, just for fun, let's try something like this. Okay, if we close this circuit and then close this switch too. Oh, okay. Don't do that in real experiment.